So if I plug this into my calculator and look at the graph, it looks something like this. Okay, so this is what we did yesterday when we talked about the graph of a derivative. So given the graph of a derivative, I want to figure out where the original function has a relative max. So I'm thinking about my sine chart. Right? My original function is going to have a relative max where the derivative changes from positive to negative. Right? So where does my where does my derivative change from positive to negative?
I want to say that's like
The negative 1 point something.
Wait, where is that? I thought that was like negative.
Where are we looking? Right here?
What is that?
Change from a positive to a negative.
Yeah.
And then do the other one. I was actually here on positive.
So yeah, it would be at this value, right? Where the derivative changes from positive to negative. Okay, this is the derivative, right? So we're just thinking about the value, not the slope. So the value changes from positive to negative right here. How do I figure out what that value is on the calculator?
You zoom in.
There's a more exact way than zooming in. Yeah, we want to use the 0 feature, right? So second trace 0, and then it asks for a point to the left, a point to the right. Guess doesn't matter. And we get 0.350 for the x value. All right, so if we're thinking about putting that value on our sine chart, right, we can see to the left of that the derivative is positive, to the right of that the derivative is negative. So this would be my local max. Right? Now, we're going to spend a couple of days doing just calculator stuff at some point after break, but I thought this one was really good with what we talked about yesterday. So are we okay with that one? Do we know how to use that 0 feature on the calculator, or is that something we'll need to?
We did it. No, we just follow it. No, we did that before. We did we did it. I remember doing it. We did do it, but I don't remember.
But we should spend some time practicing that. Okay. Okay. We will do that when we go over all the calculator stuff. All right. Then let's talk about the homework. What homework questions do we have?
3, 4,
Yes.
10, and 8.
3, 4, 10, and 8, and 7, and all of them.
7, 8.
Oh yeah, 7 is a weird one. I think I messed up something. I thought it just didn't change from.
I don't know if we have time to do all of them.
7.
7, I got positive, negative.
Because negative.
Some of
1
them
is
worked
always
out to be ugly numbers. Some of them,
Yeah, it is.
yeah. Which one was?
Because negative 1 squared and then 1 over negative 1
And make it positive.
make it a positive, so it's 0 plus 1.
Oh.
Sign chart and then do it. I don't know.
And then I still have all positives because if you put in.
No, you're not.
Yeah.
0.5.
All right.
1 over
So wait,
0.5 would be 4.
where are we starting?
It'd be 1/4. And then
Number
0.5 squared.
No, 1 over.
I'm sorry. I don't know what everyone's literally.
Well, there's usually that 7 on the front, but I need 7.
Hey, I got number 4.
All right. Let's start with 7. All right. So on number 7, if I take my derivative, let's see. This is 1/3 x cubed. So the derivative of that is just x squared.
I got it.
And the derivative of natural log of x is 1 over x. So if I set this equal to 0,
Wait a minute. Wait, what? Yeah, you're a math whiz.
Wait, why isn't there a 3 in front of the 2? Oh, she divided it by the.
3 over 3.
it.
So did we try to do quotient rule or something for that one?
Yeah.
So, I mean, this is just the same as 1/3 x cubed, right?
So much.
That was really. Yeah, I'm the embarrassed.
Yeah,
honestly.
I could literally do anything and nothing will be as embarrassing as you right now.
Are you wearing orange earrings?
No. She's not representing. That would be cute if she didn't look like that.
What do you have in your hair, bottle? Yeah, dude, they can't tell you what it is.
I was young. I'm sorry, I ripped my whole fingernail off. I don't have a nail anymore.
I do have that fingernail though. I had to, guys. I'm sorry. Do you don't think you can move anywhere in the room? I'm the one that everyone's going at. Oh, that's easy.
You mean the one that
I have to go.
Wait a minute, not more than I did, right?
Yeah, maybe.
Oh, I did that. Well, I didn't do that. Just look at the answer that I got because I did the
I FaceTimed Dinah, and this woman that got a 36 on her ACT and a perfect on her SAT told me that I did it right. So I'm upset. No, I erased all of it.
Well, I used the quotient rule, and it worked out okay.
I mean, it would, yeah.
I got plus or minus 1, so it doesn't work out.
No,
okay.
because it's cubed, not squared.
When you take the cubed root, it's sign. And any odd root is sign specific, right? Any
I know.
even root, you get plus or minus.
Everyone.
Like I said, still think you guys hate each other.
Like,
We all kind of do.
Everyone's going.
Dude, Mia,
There's table. I'm not doing it.
we were math testing last
Wait,
year, and I was
you're
punching Mia in the face because she had this. We were math testing last year, yeah, and I was punching her in the face because she had a freaking candy cane, and she like for whatever reason had to have it during the freaking test, and we could hear some stupid paper crinkling, and she finally gets it out after trying 3 times, and then she's over here just chomping, and she tosses it again on the freaking candy cane.
Never just do that.
If
Mr. Morgan, here, how do you feel about that
You
conversation?
have to.
How do you feel about your middle finger? I don't know. What do you feel?
Oh, you might not have to actually.
We do.
Why would you?
I'm safe for conflict. Well, I'm going downhill, especially.
So,
I think so.
Dinah just asked, shouldn't 0 be a critical value as well? And we want to, after we get places where our derivative equals 0, we want to look to see where the derivative is undefined. Why isn't 0 a critical value? Well, by that logic, it should be. It should be a critical value because that would make the derivative undefined. But I'm telling you it's not a critical
But that's
value.
only
Why?
one thing.
That's a good thought, but even if just one part is undefined, that makes the whole thing undefined. 0 is not part of the domain because we cannot take the natural log of 0. So-
I would never ever think that.
So just looking at the original function, I can only have values greater than 0. So 0 isn't even part of the question here. Right? So we only get one critical value. So we want to take a value less than 1, but we just figured out it has to be greater than 0, right, to plug into our derivative. So we can take a half. So a half squared minus 1 over a half. Is that positive or negative?
Negative.
That would be negative, right? Because a half squared would be a fourth. Minus 1 over a half, that would be 2. So a fourth minus 2 is negative. If I plug in something greater than 1, say 2, 2 squared minus 1 over 2 would be positive. Right? So from that, we can get all the information we need. I don't remember which things this question asked for, but we can say our function is decreasing from 0 to 1, increasing from 1 to infinity, and then we would have a local min at x equals 1. Right? Did it ask? I don't.
It asked for min max.
So did it ask for the actual y values as well?
No, it just says the same thing in all three. Look at all the.
Okay, so if it just says like locate them, that's asking where, so that's the x values. Alright, so that gives us all our information. We okay with that one? What else? Number 4.
Yeah, some kind of stuff on board.
Fourth doing it right now. Oh no, I don't do that.
Well, we did that one together, didn't we?
Oh, you did. But I didn't get that far. I just got to the.
Alright, so our derivative here, derivative of an exponential is the exponential itself, times the derivative of the exponent, times the natural log of the base, but the natural log of e is just 1, so we don't need to write that. Same thing here. So I'll set this equal to 0, and we've got negative e to the negative x plus 2 e to the 2x. So there's 2 ways to think about this. One, we could factor out a negative e to the negative x here. Okay, that's one way that we could do it.
Wait, what are their other options?
So our other option would be to just move one of these to the other side and then take the natural log of both sides.
Okay, see, I knew the other one to the other side. I just don't know what happens with the
Okay, so let's do it that way. So if I move this one over, e to the negative x equals 2e to the 2x. If this 2 weren't there, I could just drop the bases. Right, and just say negative x equals 2x. But since that 2 is there, it complicates things a little bit. So what I'm going to do is take the natural log of both sides. On this side, it's easy. The natural log of e to the negative x, I just get negative x. On the right side, it's a little bit more complicated, only because of this 2. So I'm just going to write that whole thing out for now. Natural log of 2 e to the 2x. To do it this way, we need to remember one of our properties of logs. If I'm multiplying 2 things inside of a log, so I've got 2 times e to the 2x, how can I split that up into 2 different logs?
natural log
Add
2 plus the natural log
Exactly.
of 2x.
Now what's the natural log of e to the 2x? Just 2x. So I've got negative x equals natural log of 2 plus 2x. Then we can just move that to the other side. Get negative 3x equals natural log of 2. Divide by negative 3. We get x equals natural log of 2 over negative 3. So that's my vertical value. Put that on my sign chart. Yeah. Do we want to do it the other way? Do you guys want to see the other way that we could have solved it or not? Okay. So we just want to put that value here. And then plug in a value less than and a value greater than. I don't know what that is off the top of my head, but can we at least estimate it's a negative number, obviously. Is it going to be kind of close to 0, kind of close to what numbers should we choose so that I'm definitely picking a number less than and definitely picking a greater than?
1, or it could be 0.
191.
So we know since this is negative, we can choose 0 to be a number greater than. That'll work, right? So if I plug 0 into my derivative, I've got e to the 0 plus 2 times e to the 0. Is that positive or negative? Positive, right? It would be 1 plus 2, so that's positive. How about a number less than? What negative number should I choose?
Well, -2 would be a safe bet if you didn't know exactly where it would be, or -1.
Why would that be a safe bet?
Because, I don't know. I just feel -2 is my special.
-5.
Just to be safe, I mean, -5 seems like a reasonably, really safe number, right?
Really safe.
Right? I mean, yes, I think that -2 would work, but I'm not 100% sure, right? I don't know exactly what natural log of 2 is, so let's go with -5 just to be 100% sure. So if I plug -5 in here, I've got -e to the -5th plus 2 times e to the -10th. Right? So if we write that out, we got -e to the negative.
Well, it would be
It
positive.
is
It
Yeah, positive 5th. Thank you. Plus 2e to the -10th. Is that going to be positive or negative? Is e to the positive 5th bigger or smaller than 2 times e to the -10th? Yeah, right. This is the same as -e to the 5th plus 2 over e to the 10th. Right. This is going to be a really small number. 2 over e to the 10th. Yeah, it will. So we're saying we're going to have a fairly large negative number plus a really small positive number. So that's going to get me a negative number overall. Right. So I'm changing from decreasing to increasing. My original function has a local min at natural log of 2 over -3. Right. You okay with that one? How about the graph ones? Were we okay on the graph ones?
I like the graph.
Well,
I remember their derivatives.
yes, that's the key. Any other real quick questions?
Why not now? Because he wants to get on his class and he has another paper to pass out.
That was a good one. What did you say the window was so like a chair?
Class about the Jimmy class.
Oh yeah, it seemed like you said something out of nowhere, and I was just like, oh, chair's plastic.
I wonder what I said back
I say we save this no question after this break.
No, we're not
Was
going
this
to
an
say.
ed puzzle?
No, I was planning on just teaching this today. It doesn't look like we're going to get all the way through it, though. Where is the... There it is. We might be able to. We've got 25 minutes.
Let's do the first half of the class and the second half out of this.
Yeah, I mean, as long as you guys are waiting until after... We're good with waiting until after school when I can make an ed puzzle and finish it out. I mean, I want to try to finish as much as I can right now.
Okay, teach us.
All right, so the second derivative test is what we're going to look at today. So the first derivative gave us information about the original function. We were able to figure out where the original function was increasing and decreasing and where we had local mins and maxes. The second derivative is going to give us even more information about the original function. Is that a hand? Yeah, it looked like you were raising your hand.
I was looking at my papers.
Oh, okay. So the second derivative is going to tell us where our original function is concave up, concave down, and where we have inflection points. So what that means, concave up means my function is facing up, right? A piece that looks like this is concave up. A piece that looks like this is concave down. And then a point where we change concavity from concave up to concave down or vice versa is called an inflection point. So here, we can see that this piece is facing up, right? Here, my function's concave up, then we change, and at this point, my function changes to concave down, okay? So that's the vocab for today, okay? Concave up, concave down, and then an inflection point is where we change concavity. So on this little graph here, or on these graphs, we're going to make an observation about tangent lines and concavity. So real quick, just sketch a few tangent lines around each of these graphs. Alright, so obviously in this first graph, my function is concave up. Right? What do we notice about all of our tangent lines whenever the graph is concave up?
Outside.
Well, these ones are negative.
Oh,
right?
yeah.
They're all on the outside. We could say that about this as well, right? They're all on the outside. So how could we be more
They're in the-
specific with that?
There's
It's math.
It's
I love this class. It's below the graph.
You don't know the answer.
It's below the graph.
That's
There we go.
right.
Who knows the answer?
Whenever the function is concave up, all tangent lines will be below the graph.
Oh,
So the other side then, when my function is concave down, what can I say about tangent lines? They're all above the graph. I like that it's math better.
That was so embarrassing.
If I write that on a test, will you please give me points?
I'll give you a sticker. Is that probably no points, but I'll give you a sticker.
Dragon sticker.
So close.
Alright. So the keys then are right here. If the second derivative is positive, that tells me that the graph of the original function is concave up. If the second derivative is negative, that means that the graph of the original function is concave down. So what we're going to end up doing is making a sign chart with the second derivative, okay? Exactly like we did with the first derivative. But before we jump into some of those problems, let's fill out this chart and see if we can describe what our original function would look like if we know both pieces of information about the first and second derivative. Okay, so if the first derivative is positive, what do I know about the original function? It has a positive slope, right? So we say it's increasing, right? What about if the second, or if the first derivative is negative? It's decreasing. And if the first derivative is equal to 0?
It's a max. No, wait.
Or min, or
Absolute.
that would be
Oh,
where the second derivative is 0.
I don't know how to say it.
So where the first derivative is equal to 0, we said that was a
Critical point.
critical point, right?
Oh, yeah.
So that could be a min or a max, or it could be neither of those. Right? So now we're saying if our second derivative is positive, the original function is concave up. If our second derivative is negative, then the original function is concave down. And if our second derivative equals 0,
Inflection.
it is a possible inflection point.
Why do you have to put that possible in?
Well, for the same reason here. We're not guaranteed that if the first derivative equals 0, we have a min or a max. Same reasoning here. We're not guaranteed that it's an inflection point. It's just those are the only places where an inflection point could occur. So I'm going to abbreviate point of inflection as POI. Okay, point of inflection, POI. So in these boxes then, let's sketch what a function that has these characteristics would look like. So in this box, we're going to say a function that's increasing and concave up. So that means it's going up and it's kind of cupped up, for lack of a better term, right? So that would look something like this. Okay, yeah, we're drawing examples of what this would look like. All right, so concave up and increasing. This would be an example of a function that shares both of those characteristics. So if both the first and the second derivative are positive, this is what that piece of a function would look like. Yeah, so the next one, I'm saying it's concave up and decreasing. So that's going to be like this, right? Concave up and decreasing. Let's jump to this one before we do the edges of this box. Increasing and concave down. What's that going to look like? Yeah, like that, right? How about decreasing and concave down? The opposite. That seems like a common theme. All right. So now let's fill in some of these boxes where we have either the first derivative or the second derivative equal to 0. So let's do this one first. So if my function is concave up and my critical point, and I have a critical point. My second derivative is positive. That means it's concave up, and I have a critical point. Yeah, that piece would look like a parabola. If these two things are true, if it's concave up and I have a critical point, that's going to be a relative min, right? It's going to look like this, and it's going to be at that value right there. So we can make a note here as well that this would be a relative minimum value. If the first derivative is equal to 0 and my function is concave up, that value will be a relative min. Similarly, if my function is concave down and my first derivative is equal to 0, that will be a relative max, right? That will be at this point right here. So now, let's jump down to where the second derivative is equal to 0. So if my function is increasing and I have an inflection point.
It's just like 1/2 of the point. It's a point and then
It's those two put
Yeah, right. It's kind of like these two put together, right? So we're saying it's like that point right there. Okay, my function doesn't change from as far as increasing. However, it does change concavity. Right? It would change from concave down to concave up. Similar idea here, right? It's like these two put together. So if my function is decreasing, but I have a point of inflection, right? It changes concavity.
I really want to know what we're gonna do.
So, what could happen if both of these are equal to 0? If I have a critical point,
Is it a straight line?
essentially, yeah. There are multiple things that could happen, right? If both the first derivative and the second derivative are equal to 0. But the basic idea is that it's essentially a straight line. Sharon's kind of right here, right?
She definitely just guessed. She has no idea. Okay, no, I kind of thought of it.
However, if we come across something like this on a test, I mean, they like putting small pieces like this on the AP test. We can't actually make any definitive conclusions because there are multiple things that could be happening if both of those are equal to 0. So we can just say no definitive.
No, any day.
All right, so let's try out a problem here. No.
Wait, so do we just have a second derivative?
Yes. So
There's 2x.
Here in the first, like,
No, it's x
first
squared.
the second. I don't think they do weird on the first.
No, I'm on the second derivative.
all right, so with this function here, we are going to determine multiple things. Right? It says figure out where the function is increasing, decreasing, and where it's concave up and down. So I want to use my first derivative test and my second derivative test now. So let's do what we know so far. Let's find the first derivative and use the first derivative test to determine where my function is increasing and decreasing. So what's my first derivative here? X squared minus 1. So if I set this equal to 0, I will get plus or minus 1 for my critical values. So if we put these on a sign chart,
Did you just do the second derivative right away then? Or should you do it?
well, it depends on what the question asks you to do. So here we want to use the first derivative test to figure out if it's increasing, decreasing, and then we'll use the second derivative test to figure out concavity. If it just asks about concavity, then yeah, you would just go straight to the second derivative. But here we want to figure out the stuff that we already know, increasing, decreasing. So put -1 and +1 on my sign chart, and then we'll pick values on each of those intervals to plug in. So we can plug in -2 into my derivative. If I plug in -2, that would be 4 minus 1, that's positive. If I plug in 0, plus, it would be negative. And if I plug in 2, positive. So what does this sign chart tell me about my original function?
Increasing from negative infinity to -1 and 1 to infinity. Decreasing from -1 to 1.
So increasing from -infinity to -1 and 1 to infinity, and decreasing from -1 to 1, right? So that's the stuff we already knew how to do. Now let's do the new part. Let's find the second derivative. So what's my second derivative? 2x. So now I want to set the second derivative equal to 0. This is pretty straightforward, right? We just get one possible point of inflection at 0. So now I'm going to make another sign chart. And this is why I wanted you to make sure that you are labeling your sign charts, right? If we're using the first derivative test, make sure you label it with the first derivative. If we're using the second derivative test, make sure you label it as the second derivative. Okay? So now I just want to take a value less than 0 and a value greater than 0 and plug those into my second derivative. If I plug in a negative value, this will be negative. If I plug in a positive value, this will be positive. Now, with this information, we have found that 0 is a point of inflection, right? If we change concavity, it is a point of inflection. Okay? The only time that this wouldn't be a point of inflection is if we don't change concavity. Okay? So, well, what we can say now is that our original function is concave down on this entire interval from negative infinity to 0. And it's concave up from 0 to infinity. Okay, so first derivative test tells me information about my original function, where it's increasing, decreasing, and relative mins and maxes. The second derivative test tells me where my original function is concave up and down. So,
How do you know if it's
which one's which?
I can't think of how to ask a question.
So are you trying, like, asking what the original function would look like based on this information?
Yeah.
Okay. So if I'm changing from concave down to concave up, right, it's going to do something like that, right? The other way, if we're changing from concave up to concave down, it would do something like that. So we are going to eventually get to a point where we're going to use all of this information to sketch graphs of the original function, but we're not quite there yet. All right? Questions so far? What if you just started singing? What?
Where are you, crazy?
Oh.
I just feel like I just felt looking at her and she was just like, what? Nothing.
Where did you get all that to wear?
My mom made this
No,
for me.
Bob, over here.
And my mom made me to go. So really shout out to Misty Bishop.
No, it's not a shout out to Misty Bishop. Oh my
That's my
God.
personality.
Like it needs a college boy.
I'm not a Grinch.
Okay.
Okay, moving on.
I guess I'm the Grinch since I'm going to give you homework of a break.
Exactly.
Yeah.
Sharon, he's gonna give you like ISS with things.
Alright. It's out.
I feel like if I ever did it, they'd be like,
Alma would be like, oh my gosh.
Alma would actually
No, he would get mad. Have you seen all my mad before? Used because you weren't in the bad class. I'm telling you, he hated those kids. He came in like once a week and yelled. He goes, I was driving home and thinking about how I should make you guys do all the things, but instead, I'm not going to.
Okay, so what
Moving on.
I want to learn math, guys.
Alright, so
really?
the next idea to talk about here is comparing the graphs of the original function and the derivative. So what we figured out with our last example is that my function, 1/3 x cubed minus x, has a relative maximum at -1, a relative minimum at +1, and a point of inflection at 0. Right? So this is what the graph would look like, and we will practice doing all this sketching later, right? But this is what my graph would look like, right? The function x squared minus 1, the derivative would look something like this, right? So if we examine the relationships here. We said that my original function was increasing from negative infinity to negative 1, right? So we can say on this piece, f is increasing. Well, here, right, that means that the first derivative, f prime, is positive up until we get to that value of negative 1. Then in between negative 1, 1, my first derivative is negative, right? So f prime is negative here in between negative 1, 1. Well, the slope then in between those two values on my original function is negative, right? So f is decreasing on that interval. The third interval, we can say that f is increasing, therefore from 1 to infinity, f prime is positive, right? That's kind of the idea we've already looked at. Now, what if we throw in ideas with the second derivative? Right? Figuring out where the second derivative is equal to 0. Okay, well, the second derivative is equal to 0 where we change concavity in our original function, right? So here, I can see that I change concavity. I'm changing from concave down to concave up at that point. Well, if I think about that in terms of the first derivative, at 0, what's happening at 0 on the graph of the derivative? That's true. That's a coincidence here, though. Slope changes, right? The slope changes from decreasing to increasing. If I'm given the graph of the derivative, wherever the slope equals 0, that's where the second derivative would equal 0. Okay? I will. No.